Picture a small envelope, cream-coloured, slightly wrinkled at the corners, sitting on a wooden desk in Princeton, New Jersey. The date is March 14th, 1949. Outside, the late winter light falls pale and cold across the Institute for Advanced Study, and somewhere in the building a 70-year-old man is being celebrated. It is Albert Einstein's birthday, his 70th. Colleagues have gathered. There are speeches, there is cake, and there is this envelope passed across a table by a quiet, bespectacled Austrian logician who rarely speaks at parties, who rarely attends parties at all, who has spent the last several years working on something he believes will be the most unsettling gift anyone has ever given to the author of General Relativity. The man handing over the envelope is Kurt Gödel. You may know his name. 20 years earlier, he shattered the foundations of mathematics itself, proving that any consistent system powerful enough to describe arithmetic must contain true statements it cannot prove. The incompleteness theorems, a result so devastating that the great David Hilbert reportedly fell silent when he heard it, his dream of a complete self-verifying mathematics lying in pieces at his feet. Now Gödel has turned his attention to physics, to time, to Einstein's own masterwork, and what he has discovered is, in its way, even stranger than incompleteness. The envelope contains a short paper, dense with tensor calculus, describing a new solution to the field equations of general relativity, a rotating universe, a cosmos that spins slowly on some vast invisible axis. The mathematics are flawless. Einstein himself will verify them, line by line, unable to find an error. But the implications are so disturbing that Einstein, in his written response to the Festschrift volume where Gödel's paper will be published, will describe his discomfort in language unusual for a man famous for his equanimity. He will call the result something that had already disturbed him at the time of the building up of the general theory of relativity. Because here is what Gödel found, wrapped up in that birthday envelope like a bomb disguised as a greeting card. In a rotating universe, time travel is possible. Not as science fiction, not as a thought experiment, as a mathematical certainty. Every single point in such a universe can be connected by a continuous path through space-time to its own past. You could leave your home, travel in a vast loop through the cosmos, and arrive back before you left. You could shake hands with your younger self. You could watch your own birth from a distance. And this is not a bug in the equations. It is not an artifact of some exotic, impossible scenario. Gödel derived it rigorously from the same field equations Einstein had published 3 decades before. The rotating universe is as valid a solution to general relativity as the one we appear to live in. If the mathematics allow it, then the mathematics must be asked why it allows it. And if the mathematics allow closed time-like curves everywhere, if every event can reach its own past, then what does that say about time itself? Gödel believed he knew. He believed his solution was a formal proof, as rigorous as anything in pure mathematics, that the common-sense notion of time as something that flows, time as something that objectively passes, time as a river carrying the present moment from past to future, was not merely incomplete, it was incoherent. It could not be reconciled with the laws of physics. Einstein's own theory, Gödel argued, had abolished time altogether, and Einstein had never properly faced what he had done. That is what the birthday present really was. Not just a new solution, a challenge. A question Einstein would spend the remaining 6 years of his life failing to answer. Let that settle for a moment. Tonight, we are going to follow the thread that Gödel pulled. We are going to trace the mathematics of the rotating universe, not in full rigour. You do not need a graduate degree to feel the strangeness, but carefully enough that you will understand what Gödel proved and why it matters. We are going to read Einstein's uncomfortable written response, preserved in the Festschrift for his 70th birthday, and see a great mind confronting a problem he cannot dismiss and cannot resolve. We are going to follow the decades of attempts by other physicists, Tipler, Hawking, Thorne, Penrose, to forbid such universes by fiat, to find some principle of nature that would make Gödel's cosmos impossible, and watch those attempts fail or succeed only partially. And we are going to sit with the philosophical question Gödel insisted his colleague never answered. Is time real? Not real in the sense of being measurable. Of course it is measurable. Clocks exist and they tick. But real in the deeper sense. Does time pass? Is there an objective, universe-wide now that moves from past to future? Or is that feeling, the feeling that the present moment is somehow special, that the past is fixed and the future is open, that you're moving through time the way a boat moves down a river? An illusion? A feature of your consciousness, not a feature of reality? Gödel believed his rotating universe settled the question. The mathematics proved it. Time, as we naively conceive it, does not exist. If you find these long, quiet journeys helpful, consider tapping the like button. It costs nothing and tells the algorithm that this kind of slow, careful thinking has an audience. Settle in. Let the room grow dim around you if it is evening where you are. We're going to spend a few hours in the company of two of the strangest minds of the 20th century, circling a question that neither of them could lay to rest. Now let us begin. To understand what Gödel found, you have to first understand what Einstein built. And to understand what Einstein built, you have to unlearn something about time that you have believed your entire life. Here is the thing you believe, probably without ever having put it into words. You believe that right now, this very moment, as you hear this sentence, is happening everywhere in the universe at once. You believe that whatever is happening on a planet orbiting a star in the Andromeda Galaxy is happening now, simultaneous with you listening to this. You believe that the word now picks out a single slice through reality, a cosmic instant that divides everything that has happened from everything that will happen, and that this slice is moving forward, carrying the universe from past to future like a wave rolling through existence. This is not true. Einstein proved it is not true in 1905, before he even began working on General Relativity, in the paper that would become known as Special Relativity. And the proof is not abstract. It follows from two simple observations that any careful experiment confirms. The first observation: the speed of light is the same for everyone. It does not matter how fast you're moving or in what direction. If you measure the speed of a beam of light, you will get the same number, 299,792,458 meters per second, if you're using a very good clock, regardless of your motion. This is not intuitive. If you're on a train moving at 60 miles per hour and you throw a ball forward at 30 miles per hour, a person standing on the platform will measure the ball moving at 90 miles per hour. But light does not work that way. A beam of light emitted from the front of that train will be measured at exactly the same speed by the person on the platform as by you on the train. The motion of the source does not add to or subtract from the speed of light. The second observation: the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a fancy way of saying a perspective that is not accelerating. If you're floating in deep space, far from any gravity, not firing any rockets, you're in an inertial reference frame. If you're on a train moving at constant velocity along a straight track, you're in an inertial reference frame. And the claim is that physics works the same way for both of you. There is no experiment you can perform, locked inside a windowless train car, that will tell you whether you are moving or stationary. The universe does not have a preferred state of rest. These two observations seem innocuous. They are not. Put them together, and something very strange happens to time. Imagine two observers, Alice and Bob. Alice is standing on a platform. Bob is on a train moving past her at some significant fraction of the speed of light, say 60%. As the train passes, a flash of light is emitted from the exact center of the train car, traveling outward in both directions toward the front and back walls. From Bob's perspective, the light reaches both walls simultaneously. The flash was emitted from the center. Light travels at the same speed in both directions. The walls are equidistant. The light hits both at the same moment. But Alice sees something different. From her perspective, the train is moving. The back wall is moving toward the point where the flash was emitted. The front wall is moving away. And because the speed of light is the same for Alice as it is for Bob, because light does not get pushed faster by the motion of the train, the light reaches the back wall before it reaches the front wall. From Alice's platform, those two events are not simultaneous. Stop and let that sink in. The same two events, light hitting the back wall, light hitting the front wall. For Bob, they happen at the same time. For Alice, one happens before the other. And neither perspective is wrong, neither is an illusion. Both are correct. Simultaneity itself depends on your state of motion. This is the relativity of simultaneity. It is not a theory, it is not a hypothesis. It has been verified in countless experiments over the past century, From particle accelerators to GPS satellites, it is as firm a fact as any in physics, and it demolishes the naive picture of time. Because if now is not the same for everyone, if two observers in relative motion can disagree about which events are happening simultaneously, then there is no cosmic present moment. There is no universal slice-through reality that everyone shares. The present is not a feature of the universe, it is a feature of an observer. Think about what this means. You believe right now that there is a definite fact about what is happening this instant on a planet in the Andromeda Galaxy. But there is no such fact. An observer moving relative to you might say that the event you call now on that planet has already happened. It lies in your past. Another observer moving in the opposite direction might say it has not happened yet. It lies in your future. And all three of you are correct. The present moment is not moving through the universe. The present moment does not exist as a universal feature. This was Einstein's first attack on ordinary time delivered in 1905, special relativity, a theory that unified space and time into a single four-dimensional structure, spacetime, and revealed that the separation between past and future is observer-dependent. But special relativity still preserved one crucial intuition about time. Even if simultaneity was relative, the causal order of events was not. If one event causes another, if I fire a gun and the bullet hits a target, then every observer agrees that the cause came before the effect. You can shuffle the now around, but you cannot reverse the arrow of causation. The bullet will never hit the target before the gun fires, no matter how fast you're moving. This is because, in special relativity, causal influences cannot travel faster than light, and any two events that can be connected by a light signal, or by anything slower, will occur in the same order for all observers. The past causes the future. The future is open. Even without a universal now, this much of time remained intact. Then Einstein in 1915 completed his general theory of relativity, and things got stranger. General relativity is a theory of gravity, but it is not a theory of gravity in the way Newton imagined it, as a force reaching across empty space, pulling massive objects toward each other. Einstein replaced that picture with something far more beautiful and far more disturbing. In Einstein's theory, gravity is geometry. Mass and energy do not pull on other objects. They curve the fabric of space-time itself, and objects moving through that curved space-time, planets, satellites, photons, you, follow the straightest possible paths through the curvature. What we perceive as gravity is actually the shape of the universe bending our trajectories. The mathematics of this are formidable. Einstein spent 8 years wrestling with them. The end result was a set of equations, the Einstein field equations, that relate the distribution of mass and energy in the universe to the curvature of space-time. Give me the stuff, the equations say, and I will give you the shape. The equations are simple to write down, a single line of tensor notation, elegant and compact. But solving them, finding actual space-time geometries that satisfy the equations for given distributions of matter, is ferociously difficult. Most known solutions are approximations or idealizations. A perfectly spherical, non-rotating star, an infinite uniform distribution of matter, two black holes spiraling toward each other, and here is where the trouble begins. Because the Einstein field equations do not prescribe a particular geometry of space-time. They do not say that the universe must have this structure, and not that one. They are permissive. They allow many different geometries, many different solutions, each corresponding to a different possible universe. Some of those possible universes are very much like the one we appear to inhabit. They have a cosmological history, a beginning, an expansion, a cooling. They have galaxies and stars and planets. They have a future that differs from the past. They have time that flows, and some of those possible universes are very strange indeed. In 1916, just 1 year after Einstein published the final form of his theory, the Dutch physicist Willem de Sitter found a solution describing a universe that was empty of all matter and energy, yet still expanding, driven by what we would now call a cosmological constant. In 1917, Einstein himself published a solution for a static universe, one that neither expanded nor contracted, held in perfect balance by a carefully chosen cosmological constant. In 1918, Hans Reissner and Gunnar Nordström found solutions describing charged black holes. In 1963, Roy Kerr found the solution for a rotating black hole. Each solution was a different geometry. Each geometry was a different universe. And in 1949, Kurt Gödel found the solution that contained closed time-like curves. A time-like curve, in the language of relativity, is just the path of an object through space-time, specifically an object moving slower than light. Your life, from birth to death, traces a time-like curve through the four-dimensional fabric of the cosmos. Every particle in your body has a world line, a continuous trajectory through space-time, and each of those world lines is a time-like curve. In ordinary spacetimes, the ones most physicists had studied before Gödel, time-like curves have a definite direction. They move from past to future. They are open-ended. You can trace your world line from your birth, through your childhood, through this moment right now, and onward into your future, and you will never loop back to meet yourself. Time, along your world line, is a one-way street. A closed, time-like curve is a world line that bends back on itself. A loop, a path through space-time that returns to its own starting point. A traveller on a closed time-like curve could, in principle, experience a finite proper time, aging, thinking, living, and yet arrive back at the event where they departed. They could meet their younger self. They could be present at their own past. Before Gödel, physicists had worried about this possibility in the abstract. They knew the equations did not obviously forbid it, but no one had produced a clean, exact solution that contained such curves. No one had shown that a reasonable-looking universe, with matter, with smooth geometry, with no obvious pathologies, could permit time travel as a generic feature. Gödel did. The Gödel universe is not a subtle construction. It is not hidden in the fine print of the equations. It is as explicit and as unambiguous as any solution in general relativity. Here are its properties. It is filled with matter. Dust in the technical sense, pressureless matter, evenly distributed throughout space. This dust is rotating. The entire universe turns, slowly, about every axis simultaneously, in a way that is difficult to visualize but mathematically precise. There is no expansion, no contraction. The universe is static, not in the sense of being unchanging at every location, but in the sense that its overall geometry does not evolve with time, and it has a cosmological constant, a background energy density that fills empty space. All of these features were, by 1949, unremarkable. Other solutions had dust. Other solutions had cosmological constants. Other solutions were static. What made Gödel's solution unique was its rotational structure, and the consequence that followed from that rotation. In the Gödel universe, space-time is twisted. The rotation of the matter drags the geometry itself into a kind of spiral, and that spiral allows paths through space-time that loop back on themselves. Not just at special points, not just near singularities or exotic objects, everywhere. At every event in the Gödel cosmos, there exists a closed time-like curve passing through it. Every location, every moment, can be connected to its own past. Let me try to give you a feel for how this works. Imagine you're standing in the Gödel universe, floating in space among the evenly distributed dust. You decide to take a journey, not a straight-line journey. Those stay in your ordinary future, as you would expect, but a large looping trajectory, curving out through the cosmos and then back. In ordinary space-time, such a loop would bring you back to a different time. You left at noon, you return after your long journey at 3 in the afternoon. The loop is closed in space but open in time. In the Gödel universe, because of the rotation, because of the way the geometry twists, some loops are closed in both space and time. The cosmic drag, the frame dragging of the rotating matter, bends your trajectory in such a way that when you return to your starting point in space, you also return to your starting point in time, or earlier. Depending on the size and shape of your loop, you could arrive back hours, years, or millennia before you left. The mathematics guarantee this. Gödel proved it rigorously, and here is what troubled Einstein. These loops are not marginal, they are not barely possible, they are robust, they are everywhere. The Gödel universe is saturated with the possibility of return. This is not like the situation near a rotating black hole, where exotic closed time-like curves might lurk inside the event horizon, inaccessible to external observers. In the Gödel universe, you do not need a black hole. You do not need infinite energy. You do not need a wormhole or a cosmic string or any of the exotic structures later physicists would invoke to discuss time travel. You just need to travel far enough in the right direction, and the geometry itself will carry you back. Let that settle for a moment. a valid solution to Einstein's own equations, a universe as legitimate mathematically as the one we observe, and in that universe, the past is not sealed. The past is reachable. Every event can be revisited. Every moment can be touched again. Now, before you object, and you are right to object, let me address the obvious question. Does this mean the Gödel universe is physically possible? Could such a cosmos actually exist? The answer is, probably not. Observations strongly suggest that our universe is not rotating, at least not in any way large enough to produce global frame dragging of the kind Gödel described. And our universe is expanding, which the Gödel solution does not allow. If you look at the cosmic microwave background, the faint afterglow of the Big Bang, it is isotropic to extraordinary precision, the same temperature in every direction. A rotating universe would leave a signature in that radiation, a swirl, a preferred axis. We do not see one, so we do not live in Gödel's universe. But Gödel did not care whether we lived in his universe. That was not the point. The point was that his universe was a valid solution. The equations allowed it, and if the equations allowed it, if general relativity as a mathematical structure permitted closed time-like curves, then the concept of time itself was revealed to be contingent. The passage of time, the flow from past to future, was not a necessary feature of physics. It was an accident, a coincidence of our particular cosmic geometry. In a different universe governed by the same laws, time would not pass at all. The future would be reachable from the past would be reachable from the future. The distinction would collapse, and if the distinction could collapse, if it was not logically necessary, not mathematically required, then it was not in any deep sense real. This was Gödel's argument. It was not an argument from physics alone. It was an argument from logic, from the structure of the equations, from what the mathematics permitted, and it was delivered with characteristic understatement in a short paper titled A Remark About the Relationship Between Relativity Theory and Idealistic Philosophy. The title itself is a clue. Gödel was not interested in cosmology for its own sake. He was interested in metaphysics. He had been wrestling with the question of time since his student days in Vienna, when he had studied the philosophy of Kant and the idealist tradition. And he had always believed, that time was an illusion, that the sense of passage, the feeling that the now was special, the conviction that the past was fixed and the future was open, was a feature of human consciousness, not a feature of reality. Now he had what he considered a proof. Einstein received the birthday paper with what can only be described as discomfort. We have his written response, published in the same Festschrift volume where Gödel's paper appeared. It is careful, it is measured, it is the response of a man who has checked the mathematics and found no errors, and who is therefore forced to take the conclusion seriously even though it disturbs him. Let me read you a portion of it. Einstein wrote that the problem of the now worried him seriously. He acknowledged that the experience of the now, the feeling that there is something special about the present moment, cannot be handled by physics as it currently exists. He called this problem especially painful, and that word, painful, is not a word Einstein used lightly. He went on to note that Gödel's solution had disturbed him at the time of the building up of the general theory of relativity, without at that time being able to clarify the problem satisfactorily. Do you hear what he's admitting? Einstein is saying that he knew, as early as 1915, that something like Gödel's solution might be possible. He knew that the equations might permit closed time-like curves, and he had never been able to resolve the question of what that would mean. Now Gödel had forced the issue. The solution existed. The mathematics were unimpeachable, and Einstein, in his written response, did not claim to have an answer. He did not argue that the Gödel universe was physically excluded by some principle he had discovered. He simply noted that such universes would be very strange, that they would violate our intuitions about causality, and that he hoped some additional principle might be found to forbid them. But he did not find that principle. He never found it. Einstein died in April of 1955, 6 years after receiving Gödel's birthday gift. The question of time remained open. The disturbing solution remained valid. And the man who had done more than anyone else in history to reveal the strange geometry of the cosmos never answered his friend's challenge. They walked together, you know, almost every day in those final years. Einstein and Gödel, pacing the paths of the Institute for Advanced Study, speaking in German, working through the problems that haunted them, the physicist who had bent space and time, the logician who had shattered the completeness of mathematics. Two refugees from the catastrophe of Europe, both marked by the century's darkness, both seeking something permanent beneath the flux. No one recorded those conversations. We do not know what they said to each other as they circled the grounds, as the seasons turned, as the years passed and Einstein grew older and Gödel grew stranger, more paranoid, more consumed by the fear that someone was trying to poison him. We know only that they walked, that they talked, that the question of time hung between them like an unanswered prayer, and that when Einstein died, Gödel told a colleague that he had lost his best friend, his only friend, the one person who understood. Let us pause here and make sure you feel the weight of what has been established. Kurt Gödel, one of the most rigorous logicians in history, constructed a solution to Einstein's equations in which time travel is not merely possible but ubiquitous. The solution is exact. It is not an approximation. It does not rely on exotic matter or speculative physics. It emerges directly from the mathematics of general relativity, using only dust, rotation, and a cosmological constant. In that solution, every event can be connected to its own past. There is no global time. There is no universal now. The distinction between past and future is not a feature of the laws. It is an accident of particular geometries. Gödel argued that this result demonstrated something about time itself. If the laws of physics allow universes without objective time, then objective time is not logically necessary. And if it is not logically necessary, then even in our universe, where closed time-like curves do not appear to exist, the sense that time passes is not capturing something real. It is a feature of our experience, not a feature of reality. Einstein could not refute this argument. He acknowledged its force, he expressed his discomfort, and he left the question open. In the decades since, physicists have circled back to Gödel's solution again and again. Some have tried to dismiss it. Some have tried to generalize it. Some have tried to find principles, the chronology protection conjecture, the Hawking proposal that the laws of physics conspire to prevent closed time-like curves that would somehow forbid such universes. None of these attempts have fully succeeded. The question Gödel raised is still open. What is time? Does it pass? Is there an objective now? Or is the river a mirage, and the riverbed empty, and the sense of flow a story we tell ourselves because we do not know how to live without it? We are going to sit with these questions for a while longer. We are going to trace the path from Gödel's original paper to the modern physics of time travel. We are going to meet Frank Tipler and his infinite rotating cylinder. We are going to meet Stephen Hawking and his chronology protection conjecture. We are going to see what happens when you try to forbid something that the equations permit. But first, let us go back to that envelope, to 1949. To the small office in Princeton where Einstein read his friend's gift, checked the mathematics line by line, and realized that the theory he had built contained something he had hoped it would not. The birthday party is over now, the guests have gone home, the cake has been cleared away, and Einstein sits alone with a piece of paper that tells him time might not exist. The light outside is fading, another day is ending, or seeming to end, if Gödel is right. Another slice of the present is passing, or seeming to pass. What do you do when your own theory tells you that your deepest intuition about reality is wrong? You keep walking, you keep thinking, you write a careful response admitting you have no answer, and you hope that someone, someday, will find one. The paper Gödel delivered that day was not long, 14 pages, spare, precise, almost antiseptic in its presentation. It appeared in a Festschrift volume honouring Einstein's 70th birthday, sandwiched between contributions from other luminaries. Hermann Weyl on the philosophy of mathematics, Niels Bohr on atomic physics, Max Born on statistical mechanics. Distinguished company. But Gödel's contribution was the one that kept Einstein awake. The title itself was modest. A remark on the relationship between relativity theory and idealistic philosophy. A remark. As though what followed were a footnote, a minor observation, a small clarification at the margins of a vast subject. But the remark was a blade, and the blade cut deep. Gödel began with a question that philosophers had been asking for centuries. Is time real? Not real in the way tables and chairs are real. Nobody doubted that clocks tick, that events succeed one another, that we grow old. The question was subtler. Is there an objective fact about which events are happening now? Is there a universal present that sweeps forward through the cosmos, converting future into past? Or is the now a local phenomenon, a feature of consciousness, a trick of perspective with no counterpart in the physical world? Philosophers had argued about this for millennia, but Gödel was not interested in philosophical arguments. He was interested in what the equations said, and the equations he believed said something definitive. Here is the core of his reasoning stripped to its essentials. In special relativity, the notion of simultaneity is already compromised. Two observers moving relative to each other will disagree about which distant events are happening now. An event that lies in your future might lie in my past, not because one of us is wrong, but because there is no objective fact about the matter. Simultaneity is relative. This much Einstein had established in 1905, but special relativity still preserves something. Although observers disagree about which events are simultaneous, they all agree about the causal structure of spacetime. They agree about which events can influence which other events. They agree that causes precede effects. They agree that you cannot send a signal into your own past, the light cones, those expanding surfaces that mark the boundary between events you can reach and events you cannot, are the same for everyone. General relativity generalizes this picture. Spacetime can curve, light cones can tilt, the geometry can become complicated in ways that special relativity does not allow, but the expectation, the hope, was that causal structure would remain intact. You might lose universal simultaneity, but you would keep the arrow of causation. Past would remain distinct from future. The direction of time would be written into the fabric of the universe, even if the precise slicing of that fabric into moments was not. Gödel showed that this hope was unfounded. In his rotating universe, the light cones do not merely tilt. They tilt so far that they tip over. At every point in spacetime, the boundary between future and past rotates until the two regions blur together. Paths that should lead only forward in time loop back on themselves. The causal structure that seemed so fundamental dissolves into a geometry where every event can be its own cause. Let me make this more concrete. Imagine you are a traveller in Gödel's universe. You set out from Earth, or rather from a planet in a cosmos that obeys Gödel's geometry. You do not accelerate to some impossible speed. You do not pass through any exotic portal. You simply travel along a path that the geometry permits, a time-like path, a path that a rocket with a finite fuel supply could, in principle, follow. As you travel, something strange begins to happen. The events you are passing through are not arranged in the order you expected. You are moving into regions of space-time that, back home, would have been labelled as the past, but you experience no discontinuity, no jarring transition. The journey feels continuous, even mundane. You're simply going somewhere. It is just that somewhere turns out to be when you started. Eventually you arrive back at your departure point, but in its past. You see yourself preparing to leave. You could, if you chose, wave to yourself, leave a message, change a decision. This is not a paradox in the usual sense. No law of physics is violated. The geometry permits the journey. The equations check out. The mathematics is exact. But it is a paradox in a deeper sense. A paradox of meaning. Because if you can visit your own past, then what does it mean to say that the past is past? What does it mean to say that time flows? What does it mean to say that the future is open and the past is fixed? Gödel's answer was blunt. It means nothing. These phrases are relics of intuition, not descriptions of reality. The passing of time is a psychological phenomenon, not a physical one. And the equations of general relativity, Einstein's own equations, prove it. This was the gift. This was the blade. Einstein read the paper. He checked the mathematics. He found no errors. And then he sat down to write a response. Einstein's reply appeared in the same Festschrift volume, a few pages after Gödel's contribution. It is a remarkable document. Careful, honest, and deeply uncomfortable. Einstein did not try to dismiss Gödel's solution. He could not. The mathematics was impeccable. Instead, he tried to articulate why the solution troubled him, and whether that trouble pointed to something missing from the theory. His first move was physical. Gödel's universe, Einstein noted, is not our universe. It rotates rigidly. It contains no local gravitational collapse. It does not expand. It does not match the observations that astronomers were already beginning to accumulate about the large-scale structure of the cosmos. In short, it is a solution, but not the solution. It describes a possible universe, not the actual one. This is true, but Gödel had anticipated this objection. His point was not that we live in a Gödel universe. His point was that the laws of physics allow such universes, and if the laws allow them, then the laws do not encode the passage of time. The distinction between past and future is not built into the theory. It is at best an accidental feature of particular solutions. Einstein's second move was more philosophical. He suggested that perhaps the existence of closed time-like curves indicated something incomplete about general relativity. Perhaps a fuller theory, one that incorporated quantum mechanics, or one that included additional constraints on the structure of spacetime, would rule out such pathologies. Perhaps Gödel's universe was physically possible, but not really possible, in some deeper sense that the current formalism failed to capture. This is a reasonable hope, but it is also, in a sense, an admission of defeat. Einstein was conceding that his theory, as written, permitted universes in which time travel was possible and the flow of time was an illusion. He was hoping that some future modification would save the phenomena. But he could not say what that modification would be. And here is the thing that has haunted physicists ever since. No such modification has been found. 75 years have passed since Gödel wrote his 14 pages. Quantum mechanics has been combined with special relativity to produce quantum field theory. Attempts to combine quantum mechanics with general relativity have produced string theory, loop quantum gravity, causal set theory, and a dozen other proposals. Physicists have discovered black holes, gravitational waves, the cosmic microwave background. The observational evidence for the Big Bang is overwhelming. We know far more about the actual geometry of our universe than Einstein and Gödel knew in 1949, and yet, we still do not have a principle that forbids closed time-like curves. We have solutions that avoid them. Our universe appears to be one of those solutions. The expansion of space, the absence of rigid rotation on cosmic scales, the particular distribution of matter and energy. These features seem to prevent the light cones from tipping over. Time in our cosmos appears to flow in one direction, but appears is doing a lot of work in that sentence. The laws themselves do not enforce the appearance. They permit alternatives, and the alternatives, once permitted, raise the question that Gödel insisted upon. If the laws do not require time to pass, then why do we experience it passing? This is where we must slow down. Let the question settle. Feel the strangeness of it. You are at this moment having an experience. The words you are hearing, or the thoughts you are thinking, are arriving in sequence. There is a sense of flow, a sense of becoming, a sense that the present is real in a way that the past and future are not. But according to Gödel, that sense corresponds to nothing in the physical world. The block universe, the four-dimensional spacetime that general relativity describes, simply is. All events exist together, eternally in a fixed geometric structure. The distinction between past and future is an artifact of your location and your direction of motion, not a feature of reality itself. This view is called eternalism, or the block universe view, or four-dimensionalism. It has respectable defenders. It is not a fringe position. Many physicists and philosophers accept it, at least in its broad outlines. But accepting it in the abstract is one thing. Feeling it is another. There is something almost impossible about genuinely believing that your past self, reading these words for the first time, still exists, is still having that experience. In some eternal geometric sense. That your future self, finishing this chapter, already exists, waiting to be reached. That the flow of time is a story you tell yourself, a narrative gloss on a reality that has no narrative structure at all. Gödel believed this, or at least he believed that the equations compelled this conclusion, and he found it not disturbing but liberating. If time does not pass, then change is not real in the ultimate sense, and if change is not real, then perhaps, just perhaps, the transience that makes life painful is also not real. The losses we suffer, the people we love who die, the futures that slip away from us. In the block universe, nothing is lost. Everything simply is, distributed across the fourth dimension. The people you have loved are still there, in their region of space-time. The moments you cherish are still happening in their eternal locations. You cannot revisit them, the geometry does not permit that path, but they have not vanished into nothingness. They remain. This is a strange kind of comfort, perhaps a cold comfort. But Gödel seems to have taken it seriously. In his later years, as his mental health deteriorated, as the paranoia deepened and the world became increasingly threatening, he retreated into mathematics and logic and the eternal truths that human beings discover rather than create. The Platonic realm, the world of forms, the block universe where time does not pass and nothing is truly gone. Whether this brought him peace, we cannot say. He starved himself to death in 1978, convinced that his food was poisoned, unwilling to eat unless his wife tasted it first. When she was hospitalized and could no longer perform the service, he stopped eating altogether. He weighed 65 pounds when he died. The official cause was malnutrition and inanition, complicated by personality disturbance, a tragic end. But perhaps, in Gödel's own view, not an ending at all. Merely a location, a point in the block, still there, still real, forever. We are not going to settle the question of whether Gödel was right. Philosophers are still arguing about it. Physicists are still searching for principles that might distinguish our universe's apparent temporal order from a deeper truth about the nature of time. But we're going to trace what happened next, because Gödel's solution did not remain a curiosity. It became a provocation, a challenge, a puzzle that demanded response, and the responses, when they came, were sometimes more unsettling than the original problem. The first serious attempt to generalize Gödel's result came from a physicist named Frank Tipler. Tipler was, and remains, a controversial figure. His later work veered into speculative cosmology and even theology, earning him admirers and detractors in roughly equal measure. But in the 1970s, he was a young relativist with a question: could you build a time machine? Gödel's universe was not a time machine in the engineering sense. You could not construct it. It was a global solution, a whole cosmos rotating from the beginning. You could not take a non-rotating universe and make it rotate. You could not flip a switch and create closed time-like curves. The time travel was built into the initial conditions, not something you could generate locally. Tipler wanted to know whether local time machines were possible. Could you, in a universe that did not already contain closed time-like curves, create a region of space-time in which such curves existed? Could you, in principle, build a device that would send objects into their own past? His answer, published in 1974, was conditional. If you had an infinitely long, infinitely dense rotating cylinder, a cylinder with no ends made of matter so compact that it warped space-time in just the right way, then yes, particles travelling around the cylinder could follow paths that looped back in time. The closed time-like curves would appear in the vicinity of the cylinder, created by its rotation, even if they did not exist elsewhere in the universe. An infinitely long cylinder is, of course, impossible to build. This is not a practical design. But the point was not practicality. The point was possibility. The equations of general relativity once again permitted something that intuition said should be forbidden. Time machines, or at least the space-time geometries that would function as time machines, were allowed by the laws. Tipler's paper was careful, technical and honest about its limitations. He noted that the infinite cylinder was an idealization. He explored what would happen with finite cylinders. He acknowledged that quantum effects, unaccounted for in classical general relativity, might change the picture. But the core result stood. The theory permitted time machines. This was the beginning of a literature. Over the next 2 decades, relativists explored a zoo of exotic spacetimes. Wormholes, Alcubierre warp drives, got cosmic strings. Each one raised the same uncomfortable question: does general relativity contain the seeds of time travel? And if so, what, if anything, forbids it? The most famous response came from Stephen Hawking. Hawking was, by the early 1990s, the most recognizable physicist in the world. His popular books had made him a celebrity. His work on black holes and the origin of the universe had made him a legend. And his physical condition, the motor neuron disease that had confined him to a wheelchair and robbed him of his voice, had made him a symbol of the triumph of mind over matter. In 1992, Hawking proposed what he called the chronology protection conjecture. The conjecture was simple to state and impossible to prove, The laws of physics, Hawking argued, conspire to prevent the formation of closed time-like curves. Whenever you try to build a time machine, something goes wrong. The device destroys itself. Quantum fluctuations accumulate at the boundary. The energy required becomes infinite. The universe, in short, protects chronology. It was a bold claim, and it was explicitly a conjecture, not a theorem, not a proof, not a derivation from first principles. Hawking admitted that he could not prove it. He suspected that a full theory of quantum gravity would contain the proof, but no such theory existed. What he could do was point to evidence, case studies, examples where time machines seemed to fail for one reason or another. The most compelling evidence involved something called the Cauchy horizon. This is a technical concept, but the intuition is straightforward. Imagine you're trying to build a time machine. At some moment you flip the switch. Before that moment, space-time is normal, no closed time-like curves. After that moment, your device has created a region where time loops are possible. The boundary between these two regions, the surface in space-time where the closed curves first appear, is called the Cauchy horizon, and Hawking argued that this boundary is unstable. Quantum fluctuations pile up there. Virtual particles, which ordinarily appear and disappear in tiny flickers throughout the vacuum, become amplified at the Cauchy horizon. The energy density grows without bound. The horizon itself becomes singular, a boundary of infinite curvature, a wall of fire that incinerates anything trying to cross from the normal region into the time travel region. In other words, the universe says no. This was a satisfying picture. It suggested that the laws of physics were not merely permissive but protective, that the same quantum mechanics that made particles uncertain and fields fluctuating also acted as a kind of cosmic censor, preventing the paradoxes and contradictions that time travel seemed to invite. But there was a problem. Several problems, actually. The first problem was that Hawking's argument relied on semi-classical gravity, a framework that combines classical general relativity with quantum field theory in a way that everyone agrees is incomplete. The framework works well for many purposes. It predicts Hawking radiation from black holes. It describes the fluctuations in the cosmic microwave background. But it is not a full theory of quantum gravity. It breaks down precisely in the situations where Gödel's solution and Tipler's cylinder become relevant. Situations where space-time itself is strongly curved, where the distinction between past and future becomes blurred, where the very notion of before and after loses its meaning. Maybe the instability that Hawking identified is real. Maybe quantum fluctuations do destroy time machines, but to know for sure, you would need a theory that does not yet exist. The second problem was that not all time travel spacetimes have Cauchy horizons. Gödel's universe, for instance, does not. The closed time-like curves exist everywhere, from the beginning. There is no moment of creation. There is no boundary to protect. If Hawking's argument applies only to time machines that are built, it does not apply to universes that simply are. Universes where time travel is woven into the fabric of reality from the start. The third problem was philosophical. Even if the chronology protection conjecture is true, even if quantum gravity does forbid the construction of time machines, the existence of solutions like Gödel's would still matter. The laws of physics, as we currently understand them, allow those solutions. And if the laws allow them, then Gödel's argument about the nature of time still has force. The fact that we cannot build a rotating universe does not change the fact that such a universe is mathematically possible within general relativity. And that possibility, Gödel insisted, tells us something deep about what time is, or is not. Hawking, to his credit, did not claim to have the last word. His conjecture was precisely that, a conjecture, a bet on the structure of a theory that remains unfinished, a hope that the universe is saner than the equations suggest. But the hope remains unvindicated. The equations remain what they are, and the question Gödel raised in 1949 remains open. Let that settle for a moment. For 75 years, physicists have known that the theory of general relativity, the best theory of gravity we have, the theory that describes black holes and gravitational waves and the expansion of the cosmos, permits time travel, permits universes without objective time, permits geometries where every event can be connected to its own past. For 75 years, they have searched for a principle that would forbid these possibilities. They have not found one. Maybe such a principle exists. Maybe quantum gravity will provide it. Maybe the chronology protection conjecture will be vindicated by a theory that does not yet exist. Or maybe the equations are telling us the truth. Maybe time does not pass. Maybe the flow we experience is an illusion, a feature of consciousness, a story we tell ourselves because we cannot bear to see reality as it is. Einstein never answered Gödel's challenge. He acknowledged its force. He expressed his discomfort. He hoped for future clarification. And then he died, leaving the question to his successors. His successors have not answered it either. We are still walking that path between the Institute and Einstein's house on Mercer Street. We are still circling the question that will not resolve. And the light is still fading, or seeming to fade if Gödel was right. Another day is ending, or seeming to end. Another slice of the present is passing, or seeming to pass. The physicists continue their search. The philosophers continue their arguments. And the equations sit there, patient and indifferent, containing possibilities that no one knows how to eliminate. The equations sit there, patient, indifferent. And so we must ask what those equations actually contain. Because we have spoken of Gödel's solution in general terms, rotating matter, closed time-like curves, the collapse of past and future into a single navigable landscape. But we have not yet looked inside the mathematics. We have not yet seen how the solution is built. And if we are to understand why Einstein found it so disturbing, why physicists have spent decades trying to escape its implications, we need to descend into the structure itself. Not to perform the calculations, that would take us years and a chalkboard the size of a continent, but to understand their shape, to see what Gödel saw when he sat in his office at the Institute and worked out the geometry of a universe without time. The starting point is Einstein's field equations. 10 interlocking differential equations that describe how matter curves spacetime and how spacetime tells matter where to go. They are, in a sense, a conversation, a back and forth between geometry and energy that produces the fabric of reality. On one side of the equation sits the Einstein tensor, a mathematical object that encodes the curvature of spacetime at every point. On the other side sits the stress-energy tensor, a mathematical object that encodes the distribution of matter and energy. The equations say that these two things must balance. Curvature equals energy. Geometry equals content. Finding a solution to these equations means finding a spacetime geometry that satisfies this balance everywhere. For most physical situations, this is extraordinarily difficult. The equations are non-linear, meaning that curvature feeds back into itself, that the presence of energy in one region affects the curvature in distant regions, that small changes can cascade into large consequences. Einstein himself solved only a handful of cases. The Schwarzschild solution, a non-rotating, spherically symmetric mass, what we now call a black hole. The cosmological solutions, expanding universes filled with uniform matter. Each solution was a triumph of mathematical ingenuity, a specific geometry pulled from the infinite space of possibilities. Gödel's solution added one more to the list, but his geometry was different, strange in a way that the others were not. The first thing you notice when you examine Gödel's metric, the mathematical object that encodes distances and intervals in his universe, is that it is homogeneous. Every point looks the same. There is no center, no edge, no special location. If you were placed at random somewhere in Gödel's cosmos, you would have no way of determining where you were by local measurements. The laws of physics would look identical everywhere. The density of matter would be the same. The rotation would be the same. You could be anywhere. This homogeneity is not unusual. The standard cosmological models, the ones that describe our own universe, also assume homogeneity, at least on large scales. What made Gödel's solution different was the rotation. In standard cosmology, the universe expands but does not rotate. The galaxies are receding from each other, but they are not swirling around a common center. The overall angular momentum of the cosmos is zero, or very close to it. We know this from observations. We have measured the cosmic microwave background to exquisite precision. If the universe were rotating significantly, that rotation would leave a signature, a pattern of swirls in the temperature fluctuations, a preferred direction in the sky. We do not see it. The universe, as best we can tell, is not spinning. But Gödel's equations did not describe our universe. They described a different universe, one that was mathematically possible even if not physically realized. And in that universe, everything rotated. The matter rotated around every point. The rotation was built into the fabric of spacetime itself, encoded in the off-diagonal terms of the metric tensor present everywhere and at all times. This rotation had a consequence that even Gödel did not expect when he first began his calculations. Think about what rotation means. When something rotates, different parts of it have different velocities. The edge of a spinning disk moves faster than the centre. The outer planets orbit slower than the inner ones. Rotation introduces a gradient, a difference between here and there, a variation in the direction of motion. In Gödel's universe, this gradient affected time itself. To understand how, you need to know something about the geometry of relativity. In Einstein's theory, time and space are not separate. They are woven together into a single four-dimensional fabric called spacetime. Every event, every where combined with every when, is a point in this fabric. And the paths that objects can take through spacetime are determined by its curvature. One of the most important distinctions in relativity is between time-like and space-like paths. A time-like path is one that a massive object could follow, a path that stays inside the speed of light boundary, a path that connects events in a way that allows cause to precede effect. A space-like path is one that would require faster-than-light travel, a path that connects events that cannot influence each other, events that are separated by space but not by enough time for a signal to pass between them. In ordinary spacetime, the spacetime of our everyday experience, time-like paths have a definite direction. They go from past to future. They accumulate proper time, the time measured by a clock carried along the path. They can bend and curve, can loop through space, but they cannot loop through time. You can return to the same place, but you cannot return to the same moment. What Gödel discovered was that in a rotating universe, this restriction breaks down. The rotation of the matter drags space-time along with it. This is not metaphorical, it is a physical effect, predicted by general relativity and confirmed by experiment. Near a rotating mass, space-time itself is pulled in the direction of rotation. This effect, called frame dragging, has been measured near Earth using precision gyroscopes in orbit. It is small here, almost unmeasurably small, because the Earth is barely rotating by cosmic standards. But in Gödel's universe, where everything rotates everywhere at once, the effect is total. The frame dragging in Gödel's solution is so extreme that it tilts the light cones. Light cones are the fundamental structure of causality in relativity. At every point in spacetime, you can draw a cone that represents the future, all the events that could be reached from that point by signals travelling at or below the speed of light, and you can draw another cone representing the past, all the events that could have sent signals to that point. Time-like paths are paths that stay inside these cones, always moving from past cone to future cone, never crossing the boundary. In flat spacetime, these cones point straight up, straight toward the future. In curved spacetime, they can tilt following the curvature of the geometry. But in most solutions to Einstein's equations, the tilt is gentle. The cones lean, but they never tip over so far that the future starts pointing sideways or backward. In Gödel's universe, they do. The rotation tilts the light cones progressively as you move away from any starting point. At first, the tilt is small, but as you travel farther, always moving forward according to your local sense of time, always following a time-like path, always staying inside your local light cone, the cones continue to rotate. Eventually, they tip over so far that what was the future direction is now pointing back toward your starting location. And then they tip further until the future is pointing into what was, from your original perspective, the past. Picture it. You leave home on a Tuesday. You travel outward, following a perfectly legitimate path through spacetime, never exceeding the speed of light, always moving forward according to your own watch. You make a great loop through the cosmos, billions of light years in circumference. And when you arrive at your destination, you find yourself arriving at home on Monday. You've travelled into your own past, not because you violated the laws of physics, but because the laws of physics in this particular geometry loop time itself into a closed curve. Rest with that for a moment. Every point in Gödel's universe has this property. From any event, you can draw a time-like path that returns to that event. From any moment, you can reach your own history. The closed time-like curves are not localized. They are not hidden behind event horizons or confined to extreme regions. They permeate the entire cosmos. They are everywhere. This is what Einstein saw in that handwritten paper. This is what Gödel presented as a birthday gift. Not just a mathematical curiosity, but a universe-sized demonstration that the equations of general relativity permit geometries where time loops back on itself. And Gödel's genius was not merely in finding such a solution. Others might have stumbled upon it by accident, might have noticed the closed curves and moved on to other problems. Gödel's genius was in understanding what it meant. The metric he constructed was not arbitrary, it was designed. Gödel had chosen the parameters carefully: the rate of rotation, the density of matter, the cosmological constant that Einstein himself had introduced decades earlier. These parameters were balanced against each other, tuned so that the resulting spacetime was self-consistent. The matter created the curvature created the rotation tilted the light cones, and the tilted light cones permitted the closed curves. It was a closed system, a mathematical machine that generated time travel as an inevitable consequence of its own structure. To prove that his solution was valid, Gödel had to verify that it satisfied all 10 of Einstein's field equations at every point. This required pages of calculations, substitutions, simplifications, cancellations. The off-diagonal terms of the metric created cross-terms in the curvature tensor. The rotation introduced complications that did not arise in static or expanding solutions. Every step had to be checked, every index tracked, every sign verified. When Einstein received the paper, he did not merely skim it. He worked through the mathematics himself. He checked the solution against the equations. He looked for errors that might invalidate the construction. He did not find them. The solution was correct. What he did find was something more disturbing than an error would have been. He found that his own theory, the theory he had spent a decade constructing, the theory that had overturned Newtonian gravity and predicted the bending of starlight and explained the precession of Mercury's orbit, contained possibilities he had not anticipated. The equations he had written down in 1915 did not merely describe the universe as we observe it, they described other universes as well. Universes where time runs backward, universes where cause follows effect, universes where the very notion of temporal sequence dissolves into an eternal navigable present. Einstein's discomfort was genuine. We know this from his writings, from his comments to colleagues, from the brief reply he published in response to Gödel's paper. He did not dispute the mathematics. He could not. Gödel was perhaps the only logician in the world whose rigor exceeded Einstein's own standards. Instead, Einstein questioned the physical reality of such solutions. It will be interesting to weigh, Einstein wrote, whether these are not to be excluded on physical grounds. The phrasing is careful, tentative. Einstein did not claim to know how such solutions might be excluded. He merely hoped that some physical principle would rule them out. But he did not identify that principle. He could not identify it because none was obvious. The solution satisfied all the known laws. The only objection was that it violated intuition, and Einstein, of all people, knew how unreliable intuition was when confronting the geometry of space-time. Gödel pressed the point. In his own writings, he was explicit about the implications. The existence of his solution, he argued, proved something about the nature of time. Even if our universe does not rotate, even if closed, time-like curves do not actually occur in the cosmos we inhabit, the fact that they are permitted by the fundamental laws of physics tells us that time, as we experience it, is not what we think it is. Consider, if the laws of physics allow a universe where time is circular, then time cannot be an objective feature of reality. An objective feature would be present in all possible worlds consistent with those laws. But time, in Gödel's universe, does not pass. There is no absolute distinction between earlier and later. The flow we perceive, the sense that the future is becoming the present, that the present is sliding into the past, is a feature of our particular circumstances, not a feature of reality itself. Gödel was not arguing merely that time might be different in other universes. He was arguing that the very concept of objective temporal passage is incompatible with the structure of relativistic physics. The existence of his solution was proof, in the mathematical sense, a demonstration that the equations do not distinguish between flowing time and frozen time, between a universe where moments pass and a universe where all moments simply exist, laid out in a four-dimensional block that consciousness moves through without actually changing anything. This was the argument Einstein never answered. He could have said, "Your solution requires exotic matter distributions that do not occur in nature." But Gödel would have replied that the laws do not forbid such distributions, and so the philosophical conclusion stands. He could have said, "Your solution is unstable and would collapse under perturbation." But no one knew if this was true, and even if it were, an unstable solution is still a solution, still a possibility permitted by the equations, still evidence of what the theory contains. He could have said, "Quantum mechanics will change everything." But quantum mechanics, in its standard formulation, does not provide a theory of spacetime. It rides on top of spacetime, taking the classical geometry as given. Quantum field theory, for all its successes, does not tell us what happens when light cones tip over. It breaks down precisely where Gödel's argument becomes relevant. So Einstein said nothing definitive. He acknowledged the force of the argument. He expressed his hope that physics would eventually find a way to exclude such solutions. And then he moved on to other problems: unified field theory, the foundations of quantum mechanics, the questions that occupied his final years. But Gödel did not move on. For him, the problem of time was not merely a curiosity, it was the central question. He returned to it again and again, publishing follow-up papers in 1950 and 52, each one extending and clarifying his original argument. He corresponded with philosophers and physicists, pressing his interpretation on anyone who would listen. And he waited for someone to refute him. The refutation never came. In 1950, Gödel published a paper titled Rotating Universes and General Relativity Theory. In it, he extended his analysis to a broader class of solutions: universes with different rotation rates, different matter distributions, different cosmological constants. He showed that closed, time-like curves were not a fluke of his original construction. They appeared generically in rotating cosmologies. They were, in a sense, the rule rather than the exception once rotation was introduced. He also addressed the question of physical plausibility more directly. Our universe, Gödel noted, does not appear to rotate. But the absence of observed rotation does not mean that rotation is impossible. It means only that our particular universe happens to have low or zero angular momentum. The laws of physics permit rotation. The laws permit closed time-like curves. And if the laws permit them, then the argument about the nature of time goes through regardless of whether we happen to live in a rotating universe or a non-rotating one. This is a subtle point, and it is easy to miss. Gödel was not claiming that time travel is possible in our universe. He was claiming something more abstract and more profound, that the existence of time travel solutions within general relativity reveals something about what time is. If time were objectively real, if the passage from past to future were a fundamental feature of the world, then no consistent solution to Einstein's equations would permit that passage to be circumvented. The equations would somehow forbid closed curves. They would contain, built into their structure, a protection for the temporal order. But the equations contain no such protection, and so, Gödel concluded, time as we experience it is an illusion. Einstein understood this argument. He had spent decades thinking about the nature of time, had transformed our understanding of it twice. Once with special relativity, which revealed that simultaneity is relative, and once with general relativity, which revealed that time is curved by gravity. He knew that the naive conception of time, the flowing present marching inexorably from past to future, was already undermined by his own theories. What Gödel added was the final blow, a demonstration that even the relativistic conception of time, time as the fourth dimension of a curved spacetime, does not guarantee the passage we experience. In special relativity, time is relative but still ordered. Different observers disagree about which events are simultaneous, but they agree about which events lie in the past of which other events, at least for events that can be causally connected. In general relativity, this order can be scrambled by strong gravitational fields, but most solutions preserve a global time function, a way of slicing spacetime into moments that flow in a consistent direction. Gödel's solution destroyed this. In his universe, there is no global time function. There is no way to define past and future consistently across all of spacetime. Every event is in the past of every other event if you choose the right path. Every event is also in the future. The distinction dissolves. Let me try once more to give you a feel for that. Imagine a book. An ordinary book with pages numbered from 1 to 300. You can start at page 1 and read forward, or start at page 300 and flip backward. The pages have an order. That order is fixed by the binding, by the numbers printed at the bottom, by the structure of the physical object. Now imagine a different kind of book, a ring-bound book where the pages are connected in a circle. Page 1 follows page 300. Page 2 follows page 1. You can start anywhere, read in either direction, and eventually return to your starting point. There is no first page. There is no last page. The notion of earlier and later within the book becomes meaningless, or rather it becomes local and arbitrary. Any page is earlier than any other page if you choose the right direction of reading. Gödel's universe is like the ring-bound book. Space-time wraps around on itself in the temporal direction. Every event is connected to its own past. Every moment leads eventually back to itself. The book of history has no beginning, no end, and no fixed order. This is not a failure of the equations. This is what the equations say. This is what they permit. This is the shape of space-time in a rotating universe with the parameters Gödel specified. And if the equations permit it, then the equations are telling us that time, as we understand it, is not fundamental. It is emergent. It is approximate. It is, in some deep sense, illusory. Einstein went to his grave without answering this. His successors have not answered it either. The chronology protection conjecture is a hope, not a theorem. The quantum gravity revolution remains unfinished, and Gödel's solution sits in the mathematical literature like a message from another world, patient and precise, waiting for someone to explain it away. No one has. The years after 1949 were not kind to Kurt Gödel. His mental state, always fragile, deteriorated in ways that worried even his most distant colleagues. He became convinced that refrigerators emitted poisonous gases. He believed that shadowy forces were monitoring his activities, tampering with his food, conspiring in ways that left no evidence precisely because the conspirators were so capable. He ate less and less, trusting only meals prepared by his wife Adele, and when she was hospitalized for an extended period in the late 1970s, he simply stopped eating altogether. He starved himself to death in January 1978, weighing 65 pounds at the end. The death certificate listed the cause as malnutrition and inanition, a medical term meaning exhaustion from lack of nourishment, complicated by a personality disturbance. But here is something that rarely makes it into the biographical sketches. Even in his final years, when paranoia had consumed most of his waking life, Gödel remained lucid on mathematical matters. He continued to correspond with colleagues about logic and foundations. He continued to refine his views on the nature of mathematical truth. And he never wavered on the question of time. The rotating universe solution was not a youthful indiscretion he came to regret. It was not a mathematical curiosity he set aside. Until the end, he maintained that the existence of his solution posed a genuine philosophical problem for the concept of time, a problem that had not been answered, and that he suspected could not be answered within the framework of physics alone. His colleagues, by and large, did not know what to do with this. The mathematical community had long since accepted his incompleteness theorems. The physical community had acknowledged his general relativity solution. But the philosophical conclusion he drew from that solution, that time does not really pass, that the flow we experience is a subjective overlay on a static four-dimensional structure, this they tended to set aside as a curiosity, perhaps even as a symptom of his deteriorating mental state. It was easier to admire the mathematics and ignore the metaphysics. It was easier to praise the birthday present and forget the message written inside. But the message did not go away. And in the decades after Gödel's death, a new generation of physicists began to take his challenge seriously, not because they agreed with his conclusion, but because they recognized that the equations of general relativity were more permissive than anyone had expected. Closed time-like curves were not a fluke of Gödel's particular solution. They appeared again and again in different geometries, under different conditions, as if the mathematics were trying to tell us something we did not want to hear. In 1974, Frank Tipler, a physicist at Tulane University with a taste for provocative ideas, published a paper that would become infamous in the annals of theoretical physics. He showed that if you take a cylinder of extremely dense matter and set it rotating fast enough, the space-time around it will contain closed time-like curves, not everywhere, as in Gödel's universe, but in a region near the cylinder. A spacecraft following the right trajectory around the rotating cylinder could, in principle, travel into its own past. The Tipler cylinder, as it came to be known, was not presented as a practical proposal. The cylinder would need to be infinite in length to work exactly as described, an obvious impossibility. But Tipler argued that a finite cylinder might produce similar effects, and he pushed the physics community to confront the same question Gödel had raised a quarter-century earlier. If general relativity permits time travel, what are we supposed to make of that permission? The reactions were fascinating. Some physicists embraced the challenge, exploring variations on Tipler's geometry, looking for loopholes or extensions. Others recoiled, arguing that any result permitting time travel must indicate a breakdown of the theory, a sign that general relativity was incomplete rather than revelatory. But the most consequential reaction came from Cambridge, from a physicist whose name had already become synonymous with the exotic possibilities of curved spacetime. Stephen Hawking had spent the 1970s revolutionizing our understanding of black holes. He had shown that they were not simply cosmic drains, swallowing matter and light forever, but dynamic objects that emit radiation through a subtle quantum process. He had collaborated with Roger Penrose on singularity theorems that demonstrated, with mathematical rigor, that black holes and the Big Bang were inevitable consequences of general relativity under certain conditions. And by the late 1980s, he had turned his attention to the problem of closed time-like curves, not to embrace them, but to banish them. In 1992, Hawking proposed what he called the chronology protection conjecture. The name itself is revealing. A conjecture in mathematics is a claim believed to be true but not yet proven. It sits somewhere between a guess and a theorem, demanding demonstration but lacking it. Hawking was not claiming to have solved the problem. He was claiming that a solution must exist. The chronology protection conjecture states in essence that the laws of physics must conspire to prevent the creation of closed time-like curves. Not that they do prevent them in some specific mechanism Hawking could identify, but that they must, for reasons of consistency, prevent them somehow. The universe, Hawking famously quipped, must be safe for historians. Let that phrase settle for a moment. Safe for historians. It is a joke, but it is also a philosophical position dressed in humour. Hawking was arguing that time travel paradoxes, the grandfather paradox, the bootstrap paradox, all the logical puzzles that arise when causation loops back on itself, are so threatening to the logical structure of physics that nature itself must forbid the geometries that would create them. The universe cannot allow you to kill your own grandfather, because the universe cannot abide contradictions. But here is what Hawking could not provide: a proof. 20 years later, 3 decades after that, no one has proven the chronology protection conjecture. The best attempts invoke quantum effects near would-be time machines, arguing that the vacuum fluctuations of quantum fields would become infinite at the boundary where closed time-like curves form, destroying any device before it could create them. This is called the chronology horizon, and the idea is that quantum effects serve as cosmic sensors, intervening just before causality can be violated. The problem is that these quantum calculations rely on approximations that break down precisely where they would need to be most reliable. They treat gravity classically, while treating matter quantum mechanically, a hybrid approach that everyone acknowledges is incomplete. The full answer would require a theory of quantum gravity, a unified framework that treats spacetime itself as a quantum object. And we do not have such a theory. String theory, loop quantum gravity, causal set theory. These are candidates, research programs, areas of active investigation. They are not finished physics. They cannot yet answer the question Gödel posed. So the chronology protection conjecture remains a conjecture. It is a bet on the structure of physical law, placed by one of the most brilliant physicists of the 20th century, but a bet nonetheless. And Gödel's solution remains a valid solution to general relativity, a geometry that permits time travel everywhere, at every point, along every path long enough to wind around and meet itself. The philosophical stakes here are worth pausing over. If Hawking is right, if some principle we have not yet discovered forbids closed time-like curves, then Gödel's solution is a mathematical artifact, a geometry that satisfies the equations but cannot be physically realized. It would be like a negative number of apples, coherent within the formalism, but not corresponding to anything in the actual world. Gödel would have proven only that the equations of general relativity are more permissive than nature, that the theory has solutions nature does not use. This is not unusual in physics. Many equations have solutions that are discarded on physical grounds. The question is whether we can identify the grounds. But if Hawking is wrong, if no principle forbids closed time-like curves, if the chronology protection conjecture fails, then Gödel's solution represents a genuine possibility within the structure of physical law. Not a possibility we are likely to encounter, given that our universe does not appear to be rotating in the way Gödel described, but a possibility nonetheless. And the existence of that possibility carries philosophical weight. It means that time, as we experience it, is not a necessary feature of reality. It means that the equations governing the universe do not require a global temporal order. It means that the flow of time, the sense that the present moment is fundamentally different from all others, that the past is fixed and the future is open, is not encoded in physics. This is what Gödel claimed, this is what Einstein could not refute, and this is what remains unresolved. The distinction between these two positions, Gödel's and Hawking's, might seem technical, a matter for specialists to debate in academic journals, but the implications reach far beyond physics. They touch on questions that have occupied philosophers for millennia. What is the nature of time? Does the present moment have a special status? Is the future already determined, or is it genuinely open? Are we free in any meaningful sense, or are our choices already written in the block universe of four-dimensional spacetime? Einstein himself, in a letter written after the death of his lifelong friend Michel Besso, expressed a view that aligned more closely with Gödel than with common intuition. "Now he has departed from this strange world a little ahead of me," Einstein wrote. "That means nothing. People like us who believe in physics know that the distinction between past, present and future is only a stubbornly persistent illusion. An illusion. That word again. The word Gödel used. The word Einstein used. The word that haunts these discussions because it seems to contradict everything we experience, everything we feel, everything we know directly about the nature of being alive. You're reading these words now, not a moment ago, not a moment hence, but now. The present moment feels utterly different from all others. The past feels fixed, unchangeable, a record rather than a realm. The future feels open, undetermined, a space of possibilities rather than actualities. This feeling is so fundamental to consciousness that it barely registers as a feeling. It seems like a direct perception of reality, as obvious as the colour of the sky or the solidity of the ground, and yet the equations do not support it. General Relativity describes a universe where all moments exist equally. The Big Bang is not gone. The heat death of the cosmos is not waiting. They are there, at their locations in four-dimensional space-time, no more and no less real than the moment you're experiencing now. The block universe, physicists call it. Eternalism, philosophers call it. The view from nowhere, from no particular time, from no privileged present. Gödel's contribution was to show that even within this strange picture, time retained a certain structure in most solutions, a global ordering, a universal before and after that constrained the block into something almost like a conventional history. You could not travel to your own past. You could not meet your younger self. The geometry forbade it. And this constraint, this residual order, might have seemed like a rescue of time. Not the flowing time of experience, but at least a structural time, a time of sequences and consequences. The rotating universe destroyed that rescue. It showed that the constraint was contingent, not necessary. It showed that the equations permitted geometries where even structural time dissolves, where every event is simultaneously in the past and the future of every other event, where the very notion of temporal order becomes as relative and arbitrary as the choice of which direction to call up. If such a universe is possible, if the equations admit it, then time, even structural time, is not fundamental. It is a feature of some solutions and not others. It emerges in universes like ours, where the matter distribution happens to prevent closed time-like curves, and it vanishes in universes like Gödel's, where rotation threads every event into every other event's history. This is not a proof that time is an illusion. It is a proof that time is not guaranteed, and for a concept so central to our experience of reality, so foundational to our understanding of causation and change, and the very meaning of existence, that lack of guarantee is devastating. The responses from philosophers have been varied and ongoing. some accept the block universe view wholeheartedly. They argue that the flow of time is indeed an illusion, a product of the way consciousness processes information, a useful fiction generated by brains that evolved to navigate a world of causes and effects. On this view, Gödel's solution is simply the clearest demonstration of something that was already implicit in relativity, that physics describes a static four-dimensional structure, and that our sense of temporal passage is a psychological phenomenon, not a physical one. Others resist. They argue that the experience of time is too fundamental to dismiss as illusion, that any physics which cannot account for the flow of time is thereby shown to be incomplete. The physicist Lee Smolin has been particularly vocal on this point, arguing that time is not emergent but fundamental, and that our theories of physics have gone wrong precisely by treating time as another dimension analogous to space. Gödel's solution, on this view, is not a proof that time is illusory, but a reductio ad absurdum, a demonstration that something is wrong with general relativity, or with our interpretation of it. And still others occupy a middle ground, arguing that both views capture something true, but neither captures the whole truth. The block universe describes the mathematical structure of spacetime, but that structure is not the whole of reality. Consciousness, or observation, or quantum measurement, something, introduces a distinction between past, present, and future that is real even if it is not represented in the equations. On this view, Gödel showed the limits of what physics can tell us about time, not the limits of time itself. None of these positions has won. The debate continues in philosophy departments and physics institutes around the world, and it shows no sign of resolution. Gödel's solution did exactly what he intended it to do. It forced a confrontation with a question that cannot be avoided by anyone who takes both physics and experience seriously. What is time? Why does it seem to flow? And how can we reconcile that seeming with equations that treat all moments as equally real? Einstein did not answer these questions. Hawking did not answer them. No one has. But the questions themselves have clarified over the decades, and certain paths have been closed off by the accumulating weight of evidence and argument. One path that is now clearly blocked is the hope that quantum mechanics would restore the temporal order that general relativity undermined. In the early decades of quantum theory, some physicists speculated that the irreversibility of quantum measurement, the collapse of the wave function, the transition from potentiality to actuality, might provide a physical basis for the arrow of time, a reason why the future is different from the past. But this hope has not been realized. The equations of quantum mechanics are time-symmetric. They run equally well forward and backward. The apparent irreversibility of measurement is now understood to be a consequence of decoherence, the spreading of quantum correlations into the environment, and decoherence does not restore a fundamental temporal order. It explains why we perceive an arrow of time. It does not explain why there is one. Another blocked path is the hope that cosmology would provide the answer. The Big Bang, some have argued, is the source of the arrow of time, the low-entropy initial condition from which all subsequent order and disorder flows. But this cosmological arrow explains the thermodynamic asymmetry between past and future, why eggs break but do not unbreak, why we remember yesterday but not tomorrow. It does not address Gödel's challenge, which is about the possibility of closed time-like curves, about whether temporal order is global and necessary or local and contingent. A universe with a Big Bang could still contain regions where time loops back on itself. The cosmological arrow does not forbid this. It simply does not address it. And so, the question remains open. The rotating universe solution sits in the literature, mathematically valid, physically peculiar, philosophically explosive. It was a birthday present given 76 years ago, and we have not yet figured out what to do with it. There is one more aspect of this story that deserves attention, one that speaks to the relationship between Gödel and Einstein in their final years together. After 1949, after the birthday present and the uncomfortable essay and the silent impulse over the nature of time, the two men continued their daily walks. They continued their conversations, but the topic of the rotating universe seems to have receded, replaced by other matters. The politics of the Institute, the state of physics, the encroaching illnesses of age. Einstein died in 1955, 6 years after receiving Gödel's gift. He died without resolving the puzzle. He died, one might say, inside the puzzle. A creature who experienced time as flowing, who built theories that describe time as a dimension, and who received proof that his own theories dissolved the very flow he experienced. Gödel outlived him by 23 years. In that time, he wrote occasionally about the philosophy of time, but never with the force or clarity of his 1949 paper. He watched the physics community take up his solution, analyze it, extend it, and ultimately set it aside as an exotic curiosity rather than a fundamental challenge. He watched the chronology protection conjecture emerge as a way of neutralizing his insight without actually answering it. And he maintained to the end that the question he had posed remained unanswered. In a sense, he was right. The question does remain unanswered. But the question itself has become one of the central puzzles in the philosophy of physics, a touchstone for debates about the nature of time, the interpretation of relativity, the prospects for quantum gravity, and the relationship between mathematical structures and physical reality. Gödel's birthday present has generated a literature of its own, papers and books and dissertations examining every aspect of the rotating universe, probing its implications, testing its limits. And Einstein's response, that brief, uncomfortable essay, with its admission that Gödel had posed a problem deserving serious consideration, has become a kind of landmark. It marks the moment when one of the greatest physicists of all time acknowledged that his own theory contained something he could not explain away, something that troubled him, something that suggested the very concept of time, as we understand it, might not survive the scrutiny of careful mathematical thought, the gift that cannot be refused, the question that cannot be answered, the solution that sits in the equations, patient and precise, waiting. We are not finished with Kurt Gödel's universe. There is still the matter of what it means for the future, not the future within his solution, where every point already contains its own past, but the future of physics itself, the future of our attempts to understand the cosmos we actually inhabit. Because Gödel's solution is not just a challenge to the philosophy of time, it is a challenge to the way we do physics, to the relationship between mathematical possibility and physical reality, to the question of what counts as an explanation and what counts as a mystery. That challenge takes its sharpest form in the decades after Hawking's conjecture, in the ongoing search for a theory of quantum gravity that might finally settle the matter one way or the other. And it is to that search, to the modern attempts to understand whether the universe really is safe for historians, or whether Gödel's loops lie coiled in the foundations of reality, that we must now turn our attention. The search begins with a confession of ignorance. General relativity, for all its beauty, for all its precision, for all its century of experimental triumph, is incomplete. We have known this since the 1960s, when theorists first proved that Einstein's equations, pushed to their limits, predict their own failure. Follow a massive star as it collapses, follow a universe as it contracts toward a primordial point. Follow the equations honestly, and they lead to singularities, places where curvature becomes infinite, where density becomes infinite, where the mathematics itself breaks down, and the theory has nothing more to say. At these places, general relativity shrugs. This is not a minor embarrassment. This is a fundamental incompleteness. The theory describes gravity beautifully. The bending of starlight, the precession of Mercury, the spiraling dance of neutron stars, the ripples in space-time that we now detect with laser interferometers spanning kilometers. It passes every test we throw at it, and yet it contains these holes, these places where it admits it cannot see, these singularities where the predictions become nonsense. There is another incompleteness, one that matters for our story. General relativity is a classical theory. It describes space-time as a smooth, continuous fabric, infinitely divisible, following deterministic rules without any hint of the quantum fuzziness that governs the subatomic world. But we know the subatomic world is real. We know quantum mechanics governs atoms and particles and fields, and we know, therefore, that at some sufficiently small scale, at some sufficiently extreme condition, the smooth classical picture of space-time must give way to something else, something quantum, the search for that something, for a theory of quantum gravity that combines Einstein's insights about space-time with the quantum principles that govern everything else, has consumed theoretical physics for more than half a century. String theory, loop quantum gravity, causal set theory, asymptotic safety. The list of candidates is long, and none has yet achieved the kind of experimental confirmation that would settle the matter. But this search is not separate from Gödel's challenge. It is, in a profound sense, the place where his challenge might finally be answered, or might finally be shown to be unanswerable. Let that settle for a moment. The closed time-like curves in Gödel's universe are a feature of classical general relativity. They emerge from the equations Einstein published in 1915, equations that treat spacetime as a smooth classical manifold obeying deterministic laws. If those equations are the final word on spacetime, then Gödel's loops are a genuine possibility, and the philosophical implications follow. If those equations are an approximation, if spacetime at its foundations is something quantum, something discrete, something fundamentally different from the smooth fabric Einstein imagined, then the status of those loops becomes uncertain. They might survive the transition to quantum gravity. They might emerge as genuine features of the deeper theory, vindicated and strengthened. Or they might not. They might turn out to be artifacts of the classical approximation, features that appear in the coarse-grained picture but dissolve when you look more closely. The way a photograph appears smooth from across the room but reveals itself as a grid of discrete pixels when you press your eye against it. This is the hope that animates much of the modern work on chronology protection. Not Hawking's original conjecture, which was formulated within classical and semi-classical physics. Something deeper. The hope that quantum gravity itself, when we finally understand it, will forbid closed time-like curves, not as an additional assumption, not as a conjecture imposed from outside, but as a consequence of its fundamental structure. The universe would be safe for historians not because we wish it so, not because paradoxes trouble us, but because the actual quantum fabric of spacetime simply does not permit such loops. This is an attractive vision. It would resolve the puzzle cleanly. It would vindicate Einstein's intuition and reject Gödel's challenge in the most decisive way possible. But we do not know if it is true. The honest answer, in the year you are hearing this, is that we do not know what quantum gravity says about closed time-like curves. We do not have a complete theory of quantum gravity. We have candidates, approaches, partial results. We have calculations in limiting cases. We have hints and suggestions and arguments of varying persuasiveness. What we do not have is certainty. Consider string theory, the most developed of the quantum gravity candidates. In string theory, the fundamental objects are not point particles, but tiny vibrating strings, and spacetime itself emerges from the dynamics of these strings in ways that are still being understood. String theorists have spent decades exploring the implications of their framework, calculating properties of black holes, deriving features of cosmology, searching for connections to the standard model of particle physics, and they have occasionally turned their attention to closed time-like curves. The results are intriguing but inconclusive. Some string theory calculations suggest that certain kinds of time machines are unstable, that if you try to create them, the quantum effects pile up and destroy the configuration before the loop can close. This is encouraging for chronology protection, but other calculations suggest that closed time-like curves might be consistent with string theory under certain exotic conditions. And the framework itself is sufficiently incomplete that neither result can be considered definitive. String theory has not answered Gödel's question. It has translated it into a new language, added new technical tools for exploring it, but has not resolved it. Loop quantum gravity offers a different approach. In this framework, spacetime is not a smooth continuum but a network of discrete quantum states, a kind of atomic structure underlying the apparently continuous fabric we observe at large scales. The fundamental entities are not strings but loops, hence the name. An area and volume are quantized, coming in discrete chunks rather than continuous amounts. If spacetime itself is discrete, if the smooth manifold of general relativity is an approximation that breaks down at the Planck scale, then closed time-like curves might face a different kind of obstacle. A curve that appears to close back on itself in the smooth approximation might, upon closer examination, fail to close properly when the discrete structure is taken into account. The topology that allows the loop might not survive the transition to the quantum regime. This is a possibility. Some researchers have explored it, but again, the results are partial, the calculations incomplete. Loop quantum gravity is less developed than string theory in many respects, and the question of closed time-like curves has not been definitively answered. The pattern repeats across the various approaches to quantum gravity. Each provides new tools, new perspectives, new ways of framing the question. None provides a final answer. None tells us, with the confidence we would need to close the book on Gödel's challenge, whether his rotating universe is a genuine possibility in the quantum cosmos or merely an artifact of an incomplete classical theory. Rest with that for a moment. There is a deeper issue here, one that goes beyond the technical details of string theory or loop quantum gravity. It concerns the relationship between mathematical possibility and physical reality, a relationship that has been fraught since the dawn of theoretical physics, and that Gödel's solution puts under a particularly harsh light. When Einstein published General Relativity in 1915, he provided a mathematical framework, a set of equations, a prescription for calculating the curvature of spacetime given the distribution of matter and energy. That framework turned out to describe our universe with extraordinary precision, but the framework also contains possibilities, mathematical solutions to the equations, that do not appear to describe our universe. Gödel's rotating universe is one such possibility. The equations permit it. The mathematics is consistent. The solution is as valid, in a purely formal sense, as the solution that describes our actual cosmos. But our universe does not rotate in the way Gödel's solution requires. The matter in our universe does not form closed time-like curves. We do not live inside his birthday present. So what is the status of that solution? One view says that mathematical possibility is a guide to physical possibility. If the equations permit it, then nature could in principle instantiate it, even if nature has not chosen to do so in our particular corner of reality. On this view, Gödel's universe is physically possible. It represents a way the cosmos could have been, even if it is not the way the cosmos is, and the philosophical implications follow. If time loops are physically possible, then the objective passage of time is not a fundamental feature of reality. It is a feature of our particular solution, our particular cosmic history, but not of spacetime itself. Another view says that mathematical possibility outruns physical possibility. The equations of physics are powerful tools, but they may admit solutions that nature would never instantiate, not because of additional laws we have not yet discovered, but because the mathematical framework is more permissive than reality. On this view, Gödel's universe is a mathematical curiosity, a formal construction without physical significance. The fact that it can be written down tells us nothing about what is genuinely possible in the cosmos. Einstein seems to have leaned toward the second view. His response to Gödel gestured at the difference between the cosmological solution that describes our actual universe and the solution Gödel had constructed. He suggested that the philosophical implications should be drawn from the solutions that match observation, not from the full space of mathematical possibilities. Gödel rejected this. For Gödel, the very fact that his solution was possible within the framework of general relativity was philosophically decisive. The theory itself, not any particular application of it, was what mattered, and the theory permitted time loops. Therefore, the theory denied the objective passage of time. The fact that our particular universe might not contain such loops was irrelevant to the conceptual question. This disagreement between reading physics as a description of actuality and reading physics as a revelation of possibility runs through the entire history of theoretical physics. It appears in debates about the many worlds interpretation of quantum mechanics, in arguments about the landscape of string theory solutions, in discussions of anthropic reasoning and fine-tuning. Gödel and Einstein were not having a narrow technical dispute. They were having one of the deepest disputes in the philosophy of science. And they were having it in 1949, before most of these later debates had even taken shape. The search for quantum gravity has added new dimensions to this old dispute. Because quantum gravity, if and when we find it, will presumably have its own space of possibilities, its own landscape of solutions, its own relationship between mathematical structure and physical reality. And the question of closed time-like curves will take its place within that larger question. If quantum gravity permits closed time-like curves, if some solutions to the quantum equations contain them, then Gödel's challenge survives the transition to the deeper theory. The loops may be rare, exotic, realized only under bizarre conditions, but their mere possibility would carry the same philosophical weight that Gödel claimed. If quantum gravity forbids closed time-like curves, if the quantum structure of space-time eliminates them entirely, not as an additional postulate, but as a consequence of the fundamental theory, then Gödel's challenge is finally answered. His rotating universe would stand revealed as an artifact of the classical approximation, a symptom of our incomplete understanding, a mathematical ghost that dissolves in the light of the complete theory. We do not know which of these outcomes awaits us. The research continues. Papers are published, calculations are performed, conferences convene where theorists present their partial results and argue about their implications. The question Gödel posed with his birthday present, the question of whether time is real, remains open. Let me try once more to give you a feel for what is at stake. Imagine you are a physicist in the year 2124, looking back at our era the way we look back at the physics of the 1920s. By your time, let us suppose, quantum gravity has been understood. The fundamental theory has been written down, tested against experiment, confirmed with the same confidence that general relativity and quantum mechanics enjoy in our era. In one version of this future, the fundamental theory contains no closed time-like curves. The quantum structure of spacetime, whatever form it takes, forbids them. The loops that appear in Gödel's classical solution do not survive the transition to the deeper theory, just as other features of classical physics do not survive the transition to quantum mechanics. In this future, you look back at Gödel's 1949 paper as a brilliant piece of mathematical work that revealed an important limitation of the classical approximation. His solution helped drive the search for quantum gravity by showing that the classical theory had conceptual problems, but his philosophical conclusions are understood to have been too hasty. He was reasoning from an incomplete theory. In this future, time is safe. Not because physicists declared it safe by fiat, but because the actual structure of space-time, at its deepest level, does not permit the loops that would undermine it. In another version of 2024, the fundamental theory contains closed time-like curves. They are rare. They require exotic conditions. They may never be accessible to engineering, but they are there, written into the quantum equations, as valid and as present as any other feature of the theory. In this future, Gödel is vindicated. His 1949 paper is remembered not merely as clever mathematics, but as one of the pivotal philosophical documents in the history of physics, the moment when a logician proved, using the physics of his day, that time itself is not what we thought it was. In this future, we have learned to live with the philosophical implications. Perhaps consciousness and the experience of temporal flow have been understood in new ways. Perhaps the relationship between physics and our inner lives has been reframed in ways we cannot currently imagine. Perhaps the mystery remains as deep as ever, but located differently. Not in the physics, which is settled, but in the connection between physics and experience, which is not. Which future awaits the physicists of 2124? We do not know, and this not knowing is itself part of the story. Gödel posed his challenge 76 years ago, and we have not yet resolved it. Not because we have been lazy, not because the question is trivial, but because the question leads directly into the deepest unsolved problem in fundamental physics, the nature of quantum gravity, and we are still working on that problem. The search continues, and the question waits. There is a peculiar symmetry here, one worth pausing on before we move toward the final movement of this story. Kurt Gödel built his career on demonstrating the limits of formal systems. His incompleteness theorem showed that any sufficiently powerful mathematical system, any system capable of expressing arithmetic, contains truths that the system itself cannot prove. There are statements that are true but unprovable within the system. There are limits to what formal methods can establish about themselves. This was devastating news for the foundationalist program in mathematics, for the dream that mathematics could be placed on a complete and certain foundation, every truth derivable from a fixed set of axioms by mechanical rules of inference. And now we find a similar situation in physics. General relativity is a formal system of sorts, a set of equations, a set of rules, a mathematical framework for describing space-time. Gödel showed that this system contains solutions that undermine one of our most basic intuitions, the passage of time. But when we ask whether those solutions are physically meaningful, when we ask whether quantum gravity resolves the puzzle or deepens it, we find ourselves unable to answer. The formal system of physics contains a question it cannot yet resolve. Perhaps this is coincidence, perhaps it is not. Gödel himself might have seen something fitting in the parallel. The man who showed that mathematics contains truths beyond the reach of mathematical proof also showed that physics contains possibilities beyond the reach of current physical understanding. In both cases, the formal structure opens onto something it cannot contain. The loops in Gödel's universe are not just loops in space-time, they are loops in our reasoning, circles that lead us back to where we started without ever reaching a final answer. Let that settle for a moment. The modern state of play, then, is this. Gödel's rotating universe remains a valid solution to general relativity. The physics community has analysed it extensively, understood its properties, explored its variations. No one doubts the mathematics. Hawking's chronology protection conjecture remains a conjecture. It is neither proven nor disproven. The semi-classical calculations that support it are suggestive but not decisive, and the conjecture itself has the uncomfortable flavour of a wish dressed as a prediction. Quantum gravity remains incomplete. The various candidates offer tantalising hints but no definitive answers. Some calculations suggest closed time-like curves are unstable or forbidden in the quantum regime. Others suggest they might survive. The field is in motion, the question open, and the philosophical puzzle Gödel identified, the tension between the block universe of relativity and our experience of temporal flow, remains unresolved. Physicists and philosophers continue to debate whether time is real, whether the passage of time is fundamental or emergent, whether our experience of the present moment tells us something deep about reality or merely reflects the way our brains process information. Einstein never answered Gödel's challenge, not really. His reply was careful, respectful, uneasy, and inadequate. He acknowledged the problem, he gestured at reasons for not being too troubled, but he didn't solve it. 76 years later, neither have we. The gift Gödel gave his friend sits on our collective desk, patient and precise. The solution exists. The loops exist within that solution. The universe they describe could have been our universe, as far as the mathematics is concerned. It is not our universe. Our cosmos does not rotate the way Gödel's solution requires. We do not find ourselves on closed time-like curves travelling into our own past. But the question Gödel posed is not about whether our universe happens to contain such loops. The question is about what it means that the theory permits them. The question is about the relationship between physical law and temporal reality. The question is about whether time, the flow of it, the passage of it, the distinction between past and present and future, is built into the fabric of the cosmos, or merely built into the fabric of our minds. That question does not depend on which particular universe we inhabit. It depends on the structure of the theory that describes all possible universes, and the theory permits Gödel's loops. Perhaps quantum gravity will change this. Perhaps the deeper theory will forbid what general relativity permits. Perhaps we will wake one day to the news that physicists have finally understood the quantum structure of spacetime, and that structure is incompatible with closed time-like curves, and the universe really is safe for historians, and time really does flow the way it seems to flow. Perhaps. Or perhaps the deeper theory will confirm Gödel's insight. Perhaps the loops will survive, vindicated and strengthened. Perhaps we will learn to live with the knowledge that time is not what we thought, that the apparent flow is an illusion, that the universe is static and eternal, and our sense of motion through it is a kind of misperception. Perhaps. The search continues, the equations wait. The question Gödel posed with his birthday present remains as sharp today as it was on the evening of March 14th, 1949, when Albert Einstein turned 70 and received the most troubling gift of his career. We are approaching the end of this story, but not the end of the puzzle. The puzzle has no end that we know of. What remains is to draw the threads together, to see Gödel's insight in the largest frame available to us, to ask what it means that such questions can be posed and cannot be answered. The final movement of this story concerns not just Gödel's universe, but our universe, the one we actually inhabit, the one where we seem to move through time, where memory distinguishes past from future, where we make choices that seem to matter because they shape what comes next. It concerns what Gödel's challenge means for us, for our lives, for the experience of being a conscious creature in a cosmos we do not fully understand. And so, we arrive at the final turn. You have followed this story through the mathematics of rotating dust, through the geometry of closed loops, through the philosophical argument that troubled Einstein and continues to trouble us. You have seen how a quiet logician, working alone in his office at the Institute for Advanced Study, constructed a universe that the laws of physics permit and that common sense forbids. You have watched the field respond, with admiration, with discomfort, with attempts to build fences around the forbidden territory. Now, let us step back from the technicalities and ask the question that Gödel insisted his friend never properly answered. What does it mean to experience the passage of time if time does not pass? This is not a question about physics. It is a question about the relationship between physics and experience, between the equations that describe reality and the reality we actually inhabit. It is a question about consciousness, about memory, about the felt quality of being alive in a world that seems to move. Gödel's answer was stark. Time, as we experience it, the flow, the passage, the sense that the present moment is special, that the past is gone and the future is not yet here, is an illusion, a trick of the mind, a confusion between the way things seem and the way things are. The universe, according to General Relativity, is a four-dimensional structure. All moments exist within it simultaneously. The distinction between past and future is not written into the fabric of spacetime itself. It is something we impose, something that emerges from our particular vantage point, our limited perspective, our inability to perceive the whole structure at once. Gödel did not invent this view. The block universe interpretation of relativity was already old by 1949, but Gödel sharpened it. He gave it teeth. His rotating solution demonstrated that the flow of time is not even a consistent illusion, that in some possible universes the very concept of an objective temporal ordering breaks down entirely. And if the flow of time can break down in some universes permitted by the theory, then the theory itself cannot be telling us that time really flows. The flow must be something else, something local, something contingent, something perhaps that exists only in our heads. Einstein knew this was a problem. He had known it for decades. In 1955, just weeks before his own death, Einstein wrote a letter to the family of his recently deceased friend Michel Besso. The letter contains a famous and haunting passage. Speaking of Besso's death, Einstein wrote that for those who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. A stubbornly persistent illusion. This was not a casual remark. It was Einstein's considered view, expressed in a moment of grief about the nature of time and the nature of loss. If the block universe is real, if all moments exist with equal validity, then Besso's death is not the end of Besso. Besso still exists in the eternal structure of spacetime, in all the moments that constitute his life. The fact that Einstein can no longer reach those moments, can no longer share a conversation with his old friend, is a limitation of Einstein's position in the structure, not a feature of the structure itself. This is cold comfort, perhaps, or perhaps it is the deepest comfort available. It depends on what you make of it. It depends on whether the block universe feels like a prison or a palace. But here is the question that Gödel pressed and that Einstein never answered. If the passage of time is an illusion, what is doing the experiencing? Think about that carefully. An illusion is something that appears one way but is actually another way. An optical illusion presents a static image that seems to move. A mirage presents empty air that seems to contain water. In every case, there is an experiencer who is fooled, a subject who mistakes appearance for reality. If the passage of time is an illusion, who is being fooled? The answer cannot be that consciousness is doing the experiencing, because consciousness itself is embedded in the block universe. Your consciousness is not outside space-time, watching the block from some privileged vantage. Your consciousness is part of the block. Every moment of your awareness, every thought you have ever had, every experience you will ever have, exists as a structure within the four-dimensional whole. There is no you that moves through the block experiencing one moment after another. There is only the block containing all your moments simultaneously. The sense that you are moving, that the present is special, that time flows, cannot be a property of the block itself. It must be a property of individual time slices, a local feature of how information is structured at each moment. But this leads to a puzzle that philosophers call the problem of the specious present. Why does this moment, the one you're experiencing right now as you listen to these words, feel special? Why does it feel like now rather than then or later? If all moments exist equally in the block, there's nothing that singles out this particular moment as the present. The year 2025 exists. The year 1925 exists. The year 3025 exists. All of them sit in the eternal structure of space-time, all of them equally real. And yet, from your perspective, only this moment feels present. Only this moment has the quality of nowness, of immediacy, of being the moment that actually exists. Gödel saw this as evidence that the block universe, taken seriously, leads to consequences we cannot accept. If time is an illusion, the illusion is not like other illusions. It is an illusion that has no outside, no perspective from which the illusion can be seen as an illusion. We are trapped inside the experience of passage, and the experience is so fundamental to consciousness that we cannot even coherently imagine what it would be like for the experience to be false. And yet the physics says the experience is false. The physics says the universe is static, eternal, complete. The physics says the flow of time is not a feature of reality, but a feature of how minds model reality. This is the tension Gödel identified. This is the gift he gave Einstein. This is the question that remains unanswered. Let us be precise about what Gödel did not claim. He did not claim that his rotating universe is our universe. He knew it was not. Our universe does not rotate. Our universe contains a well-defined cosmic time, at least approximately. Observers throughout our cosmos can agree on the ordering of events, at least on large scales. We do not find ourselves on closed time-like curves. But Gödel's argument did not depend on his universe being our universe. His argument depended on his universe being possible. Possible according to the laws of general relativity, the same laws that describe our universe. And if a universe without objective time flow is possible, then objective time flow cannot be a necessary feature of reality. It must be contingent. It must depend on the particular conditions that happen to obtain. This is the philosophical payload of the rotating solution. Not that time travel is possible, not that we will someday build machines that carry us into the past, but that the concept of time flow, the concept of an objective present moment that moves through the block, converting future into past, is not a deep feature of the universe. It is an accident, a happenstance, a peculiarity of the particular cosmos we inhabit. And if time flow is not a deep feature of the universe, then it cannot be a deep feature of reality. This is what Einstein never answered. He acknowledged the problem. He noted that Gödel's solution disturbed him. But he did not explain how objective time flow could be a feature of some universes but not others, if time flow is supposed to be fundamental. He did not explain what time flow even means in a framework where the very concept can be defined away by a suitable rotation of the matter distribution. In the 76 years since Gödel's paper, no one else has answered either. The attempts to answer fall into several categories, and each has its partisans. Some philosophers deny that the block universe is the correct interpretation of relativity. They argue that the equations describe a growing block, where the past is fixed and real but the future is open and indeterminate. On this view, the present moment really is special. It is the boundary between what exists and what does not yet exist. Time really does flow, in the sense that the boundary moves, new moments being added to the structure as they come into being. This view has intuitive appeal. It matches our experience of time as a process, a becoming, a continuous transformation of possibility into actuality. But it faces a severe technical challenge. The equations of general relativity do not distinguish between past and future. There is no mathematical boundary in the theory that separates what exists from what does not yet exist. The growing block must be added to the physics by hand, as an extra assumption beyond what the equations tell us. And if we add such an assumption, we must explain why it applies to our universe, but not to Gödel's universe, and that explanation is far from obvious. Other philosophers accept the block universe but deny that it eliminates the reality of time flow. They argue that the experience of passage is not an illusion, but a genuine feature of reality, even if it cannot be captured in the four-dimensional geometry. Time flows on this view, but the flow is not representable in spacetime diagrams. It is something additional, something that physics has not yet learned to describe. This view preserves our intuitions, but at a steep cost. It posits a feature of reality that is, in principle, invisible to physics. It makes the flow of time into something mystical, something beyond the reach of scientific description. Many physicists find this unacceptable. They prefer to let the equations guide their metaphysics, even when the equations lead to uncomfortable conclusions. Still other thinkers accept Gödel's conclusion entirely. Time does not flow. The passage is an illusion. The block universe is the correct picture of reality, and our experience of nowness is a kind of cognitive artifact, a feature of how brains represent information rather than a feature of the world itself. On this view, the question, why does this moment feel special, has a deflationary answer. This moment does not feel special, or rather, every moment feels special to the consciousness that exists at that moment. The you of yesterday felt that yesterday was now. The you of tomorrow will feel that tomorrow is now. Each time slice contains a consciousness that perceives itself as present. There is no global now that moves through the structure. There are only local nows scattered throughout the block, each one convinced of its own presentness. This is perhaps the most rigorous interpretation of the block universe. It takes the physics seriously and accepts the consequences. But it leaves many people deeply unsatisfied. It seems to dissolve the reality of our most basic experience into a mere trick of perspective. It makes consciousness into something like a fly trapped in amber, frozen in place but somehow convinced that it is moving. Gödel would not have minded the dissatisfaction. He was accustomed to conclusions that disturbed people. His incompleteness theorems had already shown that mathematics is stranger than mathematicians wanted to believe. His rotating universe showed that time is stranger than physicists wanted to believe. In both cases, he took the strangeness as evidence that he was on the right track. The truth he believed is often uncomfortable. Comfort is not a reliable guide to reality. And perhaps he was right. Perhaps the discomfort we feel when confronted with the block universe is not a sign that the block universe is wrong. Perhaps it is a sign that our intuitions about time are parochial, evolved for survival on a planet where memory works in one direction and entropy increases and the future is hidden. We are creatures of time in the sense that our cognition is adapted to navigating a world that seems to flow, but the world itself may not share our prejudices. This is the deepest lesson of Gödel's birthday gift. Not that time travel is possible, not that paradoxes threaten the consistency of physics, but that the concept of time, the concept we use every day, the concept that structures our language and our thought and our sense of ourselves, may not correspond to anything fundamental in the universe. The equations of general relativity describe a structure, spacetime, a four-dimensional manifold with metric properties, curved by the presence of matter and energy. Within that structure, certain paths are possible, paths that stay within the light cones, paths that respect the causal order. In most solutions, those paths run forward in time from past to future, in a consistent global direction. But in some solutions, in Gödel's solution, in Kerr's solution, in Tipler's hypothetical cylinder, the paths loop back on themselves. The causal structure permits travel into the past. The flow of time as we understand it breaks down, and the theory does not care. The theory does not say which solutions are real and which are forbidden. It gives us the equations, and the equations admit both possibilities. The universe could have been Gödel's universe, with closed time-like curves everywhere. It happens to be something else, but the fact that it could have been Gödel's universe tells us something about the nature of time that we cannot ignore. Gödel gave this insight to Einstein as a birthday present. Einstein received it with grace and discomfort. He did not deny the mathematics. He did not claim Gödel had made an error. He simply noted that the result was disturbing and expressed hope that the disturbance might somehow be contained. It has not been contained. 76 years later, the disturbance remains, and perhaps that is as it should be. Perhaps some questions are not meant to be answered. Perhaps the tension between our experience of time and the physics of space-time is not a problem to be solved, but a mystery to be inhabited. We live in time. We cannot escape it. The flow of moments is the medium of our existence, the rhythm of our consciousness, the structure of our lives. Whether that flow is real or illusory, fundamental or emergent, a feature of the cosmos or a feature of our minds, we still experience it. We still age. We still remember. We still anticipate. We still lose the people we love to death and carry them forward in memory. Einstein lost Gödel in 1978. By then, Einstein himself had been dead for 23 years, a figure frozen in the block universe at the year 1955. Gödel lived on, increasingly isolated, increasingly unwell, increasingly convinced that the world was not what it seemed. He died in Princeton, in a hospital bed, refusing to eat because he trusted no one to prepare his food. A strange end for a man who had seen so clearly into the structure of the universe. But if the block universe is real, neither of them is truly gone. Einstein still exists in the eternal structure of space-time at every moment of his life. Gödel still exists, working in his office, walking with his friend, writing the paper that would disturb a generation. The conversations they had are still happening somewhere in the block. The birthday party is still taking place. The gift is still being given. This is the promise of the block universe, if promise is the right word. Nothing is ever truly lost. The past is not erased. It is preserved, eternal and unchanging, in the fabric of reality itself. The people we have loved, the moments we have cherished, the experiences that have shaped us, all of them exist somewhere in the structure, as real as the present moment. Whether this is comforting or disturbing depends perhaps on temperament. It depends on what you make of the idea that your life is not a process but a shape, a pattern in 4 dimensions, a sculpture in space-time, complete from beginning to end, unchanging and eternal. Gödel found it comforting. He was drawn to eternity, to the idea that truth exists outside of time, that the structures of mathematics and logic are permanent and perfect. The block universe fit his sensibility. It gave him a cosmos where nothing was lost, where the past was as real as the present, where death was not an ending but simply a boundary in the structure. Einstein found it more troubling. He had spent his life trying to understand time, and Gödel's gift suggested that he had not understood it at all. The flow of time, which seemed so fundamental, might be nothing more than a perspective effect. The universe might be static. The sense of motion might be illusory. We do not know which of them was right. We do not know if time flows, or merely seems to flow. We do not know if the present moment is special, or if every moment is equally present to itself. We do not know if Gödel's universe tells us something deep about the nature of reality, or merely something deep about the mathematics of general relativity. What we know is that the question can be asked. What we know is that the physics permits the question, even demands the question. What we know is that a quiet logician, working in his Princeton office in the late 1940s, found something in the equations that disturbed one of the greatest physicists who ever lived, and we know that the disturbance has not faded. The question Gödel asked is still with us. The tension he identified is still unresolved. The puzzle he constructed as a birthday gift still sits on our collective desk, patient and precise, waiting for an answer that may never come. The night grows late, the equations wait. Somewhere in the eternal structure of space-time, a party is taking place at the Institute for Advanced Study. It is March 14th, 1949. Einstein is turning 70. His colleagues have gathered to celebrate. There is cake, there is conversation, there are tributes from the assembled luminaries. And there is a quiet man in a dark overcoat, waiting for the right moment to approach. He's holding a paper, 14 pages, a birthday gift. The gift is a universe, a possible cosmos, permitted by Einstein's own equations, a place where time runs in circles, where any event can reach its own past, where the flow of moments dissolves into a pattern that has no flow at all. The gift is a question. What is time? Does it pass? Is the present moment special, or is every moment its own present? The gift is a challenge. Einstein created General Relativity. Let him explain what it means that his theory permits worlds without objective time. Einstein will receive the gift gracefully. He will acknowledge the problem. He will gesture at reasons for not being too troubled. But he will not answer the question. He will leave the puzzle unsolved. We have inherited that puzzle. It belongs to us now. The question Gödel asked is our question. The tension he identified is the tension we live with every day, as we move through a world that seems to flow but may not flow at all. There may never be an answer, or the answer may come tomorrow, from some physicist or philosopher we have not yet heard of working on a problem that seems unrelated until suddenly it isn't. The history of science is full of such surprises. Until then, we wait. We wonder. We carry the question forward into whatever future we inhabit or whatever future is already there, waiting for us in the block. The mathematics are clear. The philosophy is not. And somewhere, in the unchanging structure of space-time, Kurt Gödel is still handing his gift to Albert Einstein. The moment is eternal. The question remains.